Now, we will discuss the graphical interpretation of phase relation between displacement, velocity and acceleration. So, our topic is graphical representation of phase relation of displacement, velocity and acceleration. So, we will draw the graph for displacement, that is y. Y is r sine omega t, and then velocity. Velocity is nothing, it is derivative of this r y. So, it is r omega cos omega t, because the derivative of sine is cos omega t and omega t is omega, derivative of omega t is omega, and acceleration is derivative of this velocity. So, it will become minus r omega square into sine omega t, because its derivative is cos omega t, derivative of cos omega t become minus sine omega t into omega. So, these are the relation or formulae which we have already proved. Now, on the basis of these formulae, we will plot the graph for these three quantities. So, this is our article, that is graphical representation of phase relation of displacement first, velocity second and acceleration third one. So, I will draw three graphs. First graph is displacement versus time. This is x axis, y axis. So, time along x axis and y displacement along y axis. Similarly, for second, it is time versus it is velocity, and third one is time versus acceleration. Now, what is the nature of the graph? We already have studied that the nature of graph is sinusoidal, because y is equal to r into sine. So, you know that the sine wave or sine function is like a wave. So, the graph of this y become sine, this one, and this r is its amplitude, this is r is amplitude, maximum value of y, and the wave is sine wave. And in the second case, in case of velocity, it is cos wave. So, what is cos wave? Cos has maximum value 1. So, cos become 1, it starts from 1 and it is like this, cos, because at 0, cos 0, 1, it starts from 1, this is maximum value, 1 means maximum value. And what is the maximum value? This is amplitude. So, maximum value is r omega, it is r omega. So, this line is somewhat greater than this line, because it is only r and it is r multiply with omega. So, it is more than first line. So, this wave has greater amplitude, and the nature of wave is cos wave, because it is cos function. And in case of third, acceleration is again sine function. First is also sine and third is also sine, but there is negative sign, so it is minus sign. So, what is the graph for minus sign? So, you know that the graph for minus sign is, so I will draw this graph separately here. So, this one is the graph acceleration versus time origin, and graph is minus sign. So, what is minus sign? Sign always starts from 0, sin 0 0, that is 0, and but minus sign. So, we know that in case of plus sign, the first half is positive, but in case of negative sign, the first half is negative, and this one. So, this is minus sine wave, and this is amplitude. So what is amplitude? This is a height or peak. So this peak is r omega square, r omega square. So this is called displacement amplitude, this one is called velocity amplitude, and this one is called acceleration amplitude. Amplitude means the height of the wave. So this graph is shorter in height, it is greater and it is greatest, the highest peak, r omega square. It is only r. Let the value for r is, let it be 10. So it is 10 into omega. It is 10 into omega square. So it is greater. So in this way, we can represent all the variables y, velocity and acceleration in terms of graphs. So it is called graphical representation of the phase relation or angles. Now, next, now we will find or discuss different types of oscillators. We will find or discuss different types of oscillators. Oscillators. So in the whole book, we will discuss two types of oscillators. Two types. We will discuss two types of oscillators. First one is mechanical oscillator, and second one is electrical oscillator. Mechanical and electrical. So mechanical, in which we apply force or any torque on the system, and in electrical we will give electricity or electric current for the oscillator, for the motion of oscillator. So mechanical and electrical. Further, we will study first of all mechanical oscillator. So in this chapter, our first part is first mechanical oscillator. Mechanical oscillator. So we will study three mechanical oscillators in this chapter. Three. First one is spring mass system or oscillator. Spring mass system or spring mass oscillator. So it consists of spring and mass. And second one is compound pendulum. Compound pendulum. And third one is torsional pendulum. Torsional pendulum. And another fourth is also discussed in this book. So you may be studied that vibration of the mass in a string. Vibration of mass in a string means the motion of the string is also vibratory motion. So mainly there are four types of mechanical oscillator which we will study. So main, first, second, third, these are important. So you know that you are already familiar with first oscillator, spring mass oscillator. So in all oscillators, we will prove that the motion of the oscillator is harmonic. First one is to prove the motion is harmonic. And second one, if the motion is harmonic, then we have to prove the time period or frequency of that oscillator. So there are our two aims in all cases. So first of all, I will discuss spring mass oscillator or spring mass system. It is also called simple harmonic mechanical oscillator. Simple harmonic mechanical oscillator, that is spring mass. And after that, we will study compound, then torsional, then vibration of a mass in string. So, we will solve it one by one. The first of all, spring mass system. In all cases, I have already told you that we will find two answers. There are two conclusions, two results which we will obtain for these cases. First one, the motion is simple harmonic motion. First we have to prove the motion is SHM. And second one, we have to find the time period of the oscillator. So, if the oscillator is moving in simple harmonic motion, then it must have some time period. So, there are two main results which we will find in all cases. So, how we prove that the motion is harmonic? If the equation is just like this, d square upon d square y upon dt square is equal to minus omega square y. If this equation is obtained, we can say that the motion is harmonic, because this is the equation which is proved in case of acceleration, because it is acceleration, d square y upon dt square, that is acceleration. So, acceleration is equal to minus omega square y. So, we have to prove firstly this formula, because this formula is true only in oscillators or harmonic oscillators. Then we have to find time period. So, we will discuss in detail. So, what is spring mass oscillator? So, from the meaning spring mass, it is clear that it consists of a spring and a mass m is attached with it. So, this is spring mass problem or spring mass oscillator. So, let it is a table. A mass m is attached with the spring and the one end of the spring is tied with the wall. When we pull this mass towards right side, then spring will expand, and after that, after some time after pulling, we will keep it free, then it will automatically came back in the reverse direction. So, the motion of the mass become harmonic. So, there is harmonicity in the motion of the mass with respect to spring. So, this is spring mass oscillator. So, there is spring having stiffness S. We know there is stiffness property of the spring. Spring may be contracted or may be expanded. So, that property which contract or expand the spring is called stiffness property. So, let S be the stiffness constant of spring and m be the mass. So, spring mass problem means Sm problem, simple. Now, we have to derive the equation for spring and mass. So, for spring, we know that in case of spring, F is equal to minus S into x. So, this formula, this is called Hooke's law. Hooke's law. You have already studied in lower classes Hooke's law. What is Hooke's law? The force acting on the spring is always proportional to displacement. So, I am writing the displacement as x. So, x means this is the displacement, that is x. So, F is equal to x and F is equal to minus Sx. It is minus Kx or maybe minus Sx. So, I have written this spring constant as S, and minus sign, it is for restoring force. So, this is restoring force. And second, for mass, this F is equal to ma. This is second equation. So, there are two forces acting on these two systems. The mass acting on the force acting on the mass is F is equal to ma. You have read this formula in Newton's second law, because it consists of mass. So, it is responsible for mass, and F is equal to minus Sx, it is for spring. So, it is spring formula. So, there are two forces. This force F is equal to ma, it is positive, and F is equal to minus Sx, it is negative force. So, why it is negative? Because it is restoring. This force provides restoring action on the mass. So, when you pull this mass on the right hand side, then which force is responsible to come back its main position. So the reverse force is provided by the spring, and applied force is mass. So this is called applied force, or it is called deforming force, deforming or applied force. This force is applied by us, and it is a restoring force. Restoring force. So you may remember these two forces as deforming force and restoring force. For spring, it is a restoring force. Restoring force. And for mass, it is deforming force. Now, compare these two forces, 1 and 2. Compare equation number 1 and 2. You will get this MA is equal to minus SX. So I am writing the displacement as X. So what is A? A become minus S upon M into X. Is it clear? So in this equation, this A is equal to minus omega square x. So this equation is valid for simple harmonic motion, which we have already studied, proved. So compare this acceleration with this acceleration. So this is acceleration obtained from spring mass problem, and this is standard formula for SHM. So on comparing AA, x or y or x may be displacement, and this omega square is equal to S by M. So this is, it is nothing, it is omega square, and we compare it with the standard equation, and minus with minus. So omega become S by M under root. Okay, and omega is 2 pi by t, it is S by M under root, and t become, this implies t become 2 pi into M by S. So this is expression for time period of spring mass problem or simple harmonic mechanical oscillator. And from here it is clear that it satisfies the equation of simple harmonic motion equation, therefore the motion is harmonic. So these are the two answers or two results which we obtain from this problem. So this shows A is equal to minus any constant into x. This is equation for SHM. So this equation proves that the motion is harmonic motion. Harmonic motion. And the time period for this harmonicity is this. So we will prove these two formulae in all cases, in all type of oscillators. Firstly, we have to prove SHM equation. Secondly, we have to prove the time period. So thank you very much.